separately, like outside the cloud, if somebody wants to have as like a private setup. Okay, so where they can run the models and do all the computations in a local setup rather than going to the cloud. Okay, so let's see them. As you know that big data we have already covered. We have covered in fact five V's. So I need to update this. Okay, veracity, type, all those things. Volume, veracity, variety, veracity, value. Okay. So we have seen this already. Okay, so there is nothing new here. What is the typical big data workload, the use cases, how it handles the sources, data sources, what are the different phases of um, the big data, then advantages, purpose. You have seen everything, like the five V's, everything. So we'll move on. So this may be new to you, unless you have studied in cloud computing. Okay, in some universities, some syllabus it covers, in some cloud computing syllabus it's not. So let's anyway we'll have to revisit it as per our syllabus. So you all heard about the GPUs. You probably would have used GPUs for your projects in UG level, or you may be using it for internship and so on. So GPUs are, of course, very much needed. They are having thousands and thousands of cores in the hardware. Okay, so they are able to do a lot of parallel tasks. So that is why GPUs are used mainly for image processing and to run massively uh, parallel computing tasks. Okay, so where CPUs cannot meet the demand. Okay, so because and then the GPUs generally are manufactured by all these high-tech companies like Nvidia and other companies, right? They all um, focus on speed and efficiency. Second. Okay, so that's the main goal, and to, of course, to reduce the cost and to package more and more cores in a chip. So that's what they're all striving for. So why do we need this parallel computing? Because we have various types of parallelisms. Okay, so we are now talking about huge or humongous data set sizes, right? So where the data parallelism uh, is done or is required. So where the huge data is split into various chunks of smaller data, smaller chunks of data. All right, and they are each chunk is executed on different cores or different CPUs. So it could be different CPUs on the same system. It could be same. It could be different CPUs on different systems, or it could be using GPUs, one GPU or multiple GPUs on different systems. All those things are possible. Okay. So cloud also provides a GPU environment. Okay, and they provide managed service, unmanaged service, everything. Okay, so that is the reason they go with cloud, because you don't want to invest in GPUs and other hardware, okay, to do data parallelism. The task parallelism, as the name suggests, the data sets may be broken down into some smaller data sets, smaller chunks of data. But the tasks, right, like mapper tasks, reducer tasks, so those tasks have to be run in parallel. So in the first case, the data is broken down into smaller chunks and then they are uh, manipulated, or they are handled or computed. In the second case, the task, various types of tasks, they can be run in parallel. Okay, so it's like threads in operating system. So each thread can do a particular task or run a particular task. So here, the task for task parallelism, you need parallel computing, for which you need hardware support as well. Then the pipeline parallelism, where you have to do certain uh, tasks. You have to complete it as a pipeline. So it is not single task. So there are several steps or stages involved. It's like end-to-end task where you have to complete it in one go, okay, to get the result. So that is the pipeline parallelism. So we have requirement to parallelize various activities, data, tasks, and pipeline. So that's why parallel computing is it's extremely important, and it is being it's in demand also. Okay, apart from distributed computing, in distributed computing, of course, you are also using distributed resources, all right, but you don't require this massive parallelism, okay, which is needed in parallel computing. Here they will be running in parallel just to utilize the resources or to spread the workload across various systems for scalability, for fault tolerance. So if one node is down or there's some issue with one um, node, right? Or some processes getting stuck in one node and so on, the other processes will be able to run, or they can even build a standby system and so on. So that is part of fault tolerance. So they'll build fault tolerance systems, okay, to handle all the failures. And where here data locality is essential. So essentially the data will be local, and it will use the local resources on that particular server. So basically data is getting moved across various servers, which is expensive, which is not good for certain application, because you are moving large amount of data to various systems and then running the tasks. Okay, so movement of data should be restricted. So, but that is the disadvantage of distributed computing. Data should be local, and it has to be moved to various distributed nodes. But advantage is large data sets can be distributed, and they all can be uh, handled in parallel, and you don't have single point of failure. It will even set up replicas and so on. So if one of them fails, the other one will be able to deliver the results. So the replicas can be set up to avoid single point of failures. Okay, and then it also supports horizontal scaling. So where you can add more and more resources horizontally, not vertical scaling. Okay, not bumping up or increasing the capacity of individual server. That is the vertical scaling. Horizontal scaling, it will be adding more and more servers and resources in a horizontal manner. Okay, then so here that's where we look at various types of computing which we have already seen. Okay, cluster computing. Then examples are also given, like Hadoop clusters, Spark clusters, which we will look at it slowly. Cloud computing, you're already familiar. I explained grid computing a little bit. So where there is federation of heterogeneous resources. So federation is nothing but a group of people, companies, they're all coming together. Is that, yeah. So the group of companies, generally companies, not users, but users can be belonging to different domains, expertise, and networks, and so on. So generally, it's a federation of heterogeneous resources that is provided by a group of companies. They all come together and pull in the resources and run a project. Okay, batch jobs. Then edge computing, I mentioned it earlier. So where the data sources are processed in the edge services, could be server in the edge server in the network, or the server closest to the client, to the users and client. Okay, so so that you don't have to do a lot of processing in the core, and then move the results back to the client. So the processing is already done closer to the client, and then the results are available almost instantly. Okay, so edge computing is also very popular these days. Then we have other storage models. Hadoop we will see later, maybe in the next class only, not today. Then the different types of file systems used. HDFS is very popular because it can handle large amount of data set. So it beats all other file systems in terms of scalability and of course performance as well. So there is another Google file system which is not in scope for us, Ceph file system which is not in scope for us. So Ceph is another framework or a platform which supports Ceph file system. So basically it is compatible with POSIX standard, the portable operating system interface standard. Okay. So if you want to know a little bit more about Ceph, FS and Google file system, differences and so on, you can look at the notes section. So as I told you yesterday, you always refer to the details in the notes section, which will have additional information, which may or may not be expected for the exam. Okay, certain things may you are expected to know, which is not in the slide. So it may a small weightage is given to the notes section as well for the exam. Okay, so Ceph is uses a distributed object store, just like AWS and other cloud platforms. They use object store, right? So this also uses an object store or distributed object store to store the data. So just like you have NTFS, then the Linux file system, XFS, what else? There are different file systems. So like that, you have HDFS, FS, GFS, and so on. Okay, they all have different format, different interface, different commands to manage the file storage. Okay, so you can look at the references here for additional information. Okay, then you have also NoSQL distributed databases. You're already familiar with MongoDB and so on, Cassandra or Hadoop base. We will cover it in this course. Okay, then they all deal with partitioning, replication, everything at the database level. All right, so it's a NoSQL distributed database. All right, so to handle large amount of data, but they don't compare with HDFS. HDFS will beat any other distributed file system. That's why it's popular. But you need that Hadoop framework on which HDFS will work. Okay, if somebody can manage with, or if they need NoSQL distributed databases, they have to go with these choices that are listed here. Then you've already studied about eventual consistency, strong consistency, and so on. If you have not studied, read up on that. It will be very useful for you, even for interviews and for your job. Where I'll just give a quick one-line description. Where you all know about data consistency across all the replicas. Okay, the data should be consistent across all the replicas. So just to give you an example, if you're doing a bank transaction, if you are doing, let's say, credit transaction, let's say your transaction of 10,000 rupees, credit goes to server 1 or storage 1, that has to be quickly synced up or replicated across the distributed networks. Because next time you do a debit transaction, it should, and your debit transaction can be connected to any server in the distributed system, any storage, any server. So you should be able to see your previous credit transaction. Otherwise, you won't be able to use that 10,000 rupees which you credited online. So if there is latency or if there is no proper consistency. So the strong consistency means the data will be immediately available across the replicas, which means it will do concurrent writes. So the 10,000 credit will go to server 1, server 2, server 3, or replica 1, replica 2, replica 3 almost at the same time. Whereas eventual consistency, it will go to, the writes will go to um, one replica or one storage. Then the that particular data changes will be eventually synced up with other replicas. That is eventual consistency, which means there will be some latency before you can see the recent transactions. Is it clear? If it is not clear, ask me now, or you have to read up on this. It will be very useful to you. Because this is all cloud basic concepts. We can't be explaining this in all right. Then there are other models just for illustration purpose. So where parallel computing is used heavily, this OpenMP architecture, open multiprocessor architecture, pre-threads also, POSIX threads, multi-threading, where you need to have shared memory concept, right? Where shared memory will be used. So their parallel tasks will be running. They all will be using the shared data. How they compete for the shared data or updating the shared memory, all those things will be part of the parallel computing. Even in distributed system, right? They may be different tasks will be running in parallel, and they may be sharing shared memory or shared data. Okay, but generally in distributed computing where there are many servers involved, the data will be local, memory will be local, so they don't have to connect to memory or use memory of another server. Okay, but operating system itself supports CPU support using memory of another CPU. You know that each CPU has its own cache or memory. So OS and CPU themselves support CPUs using memory belonging to another CPU. So those things are all supported in the hardware. Intel, AMD, they all support. Okay, but in general, this shared programming will not apply for distributed computing, but for parallel programming models, where different programs are running in parallel on the same server, and they have to share the memory and other resources on a single host. Then yesterday we briefly saw this message passing interface, okay, and high performance computing. So all these are use cases or models available for parallel programming. Okay, then there is CUDA, and some of you might have heard. Okay, this is from NVIDIA. So where it provides a GPU grid. Okay, the CUDA is Compute Unified Device Architecture, where it provides a GPU grid for running programs in parallel. This is for parallel computing. Okay, then OpenCL, Open Computing Language from Apple. Then for deep learning workload, metric operation, there are so many models already available, provided by different companies and also as open source. Of course, CUDA and all those things are paid ones from paid hardware and software from NVIDIA. But there are so many other models, open source models available. They also can be used. If you are interested to know more about CUDA and GPUs and so on, just look at the notes section. Okay, I put sufficient, I think, information. That is enough. Let me see how much information is there. Second. GPU, CUDA. Yeah, this link and this information sufficient. Okay, to know about CUDA and GPU. Okay, now let's see what else is there. Yeah, there are some distributed um, programming models, just like parallel programming models. So that's what is more interesting and relevant for this course, big data analytics. Okay, we don't bother much about parallel programming models. We want to see or learn about distributed programming models, which are relevant for big data analytics. So MapReduce, which we will see in the upcoming classes. Okay, so where a large uh, task or data is broken down into parallel tasks, and they all are generating some intermediate results and steps. Okay, there'll be a lot of shuffling, sorting, everything of the intermediate results, that is intermediate values or results. And then finally, the reducer processes will run after the mapper processes are done to aggregate those results that were uh, generated by various mapper processes. So this we will see. This is the we will see word count example and all those things. Okay, so where if you have data set, a large data set, let's say it's a text file. Okay, where you have to count the occurrence of a specific word. All right. So let's take some academic related example where you have large student records with result information. Okay, some semester results information, subject wise, and so on. So where we have to uh, look for a specific word. The word could be need not be student name. It can be something else, right? Could be GPA related. It could be uh, pass fail kind of information, fee related information, absentees, students were absent for the exam. So lots of uh, words may be required to be counted for various reasons. So that is one. Then of course, when you talk about financial data and healthcare data and so on, so where you can use this word count program to count the occurrence of the same word, occurrences of the same word, and where MapReduce will be very useful. So we are talking about large data. Okay, so that is very common word count program. All right, then Spark is of course using something called in-memory computation that I explained it yesterday. Um, let's see, it's here. I'll just quickly show it. Oh, I think it's after this. Yeah. So this is what I explained yesterday. Yeah, this in-memory computation where large amount of memory or memory grid, that is grid of real memory, that is physical memory. They are used for all computations as well as for storage until the persistent store is needed. That is, the data should or result should be stored permanently. Until then, it's stays in memory, and then the data is pushed to persistent storage. So you get faster results, better performance, reduce latency, and so on and so forth. Lots of advantages I explained yesterday. The only disadvantage is the cost of the physical memory grid, because it's not even though memory is cheap, but you're talking about um, terabytes of data, so where you have to pull in so much of memory. Okay, so Spark uses it, and then there are other models also like support SQL, ML, graph processing. They all use this so-called DAG model, directed acyclic graph. So you all must have studied this DAG. Otherwise, it's good to refresh it. Okay, when you get a chance. So they are directed graphs, and there is no cycle. That's why cycle formed in a, there is no loop or a cycle formed in the graph. There are acyclic. So acyclic or acyclic directed acyclic graph. So then the stream processing, which we will study in the subsequent models, subsequent modules. So Spark, Flink, Kafka, Storm. Kafka, I don't think we'll focus here. Maybe a little bit only. Okay, so other we look at other stream processing models to handle data stream. audio stream, text stream, video stream, and so on. Okay, and where they are used, basically they're used in social media, everywhere, IoT, fraud detection, everywhere. With the stream-based processing models, where the data is coming from different sources, that is distributed sources, and they are also stored in distributed storage. All right. How many more are there? Yeah, just another three slides. Then big data platform. So we'll look at all of them in the subsequent classes. Okay, like Hadoop, which basically it's an ecosystem. Hadoop ecosystem has all these tools and applications like HDFS, MapReduce, Yarn. Yarn is the resource navigator, yet another resource navigator to manage all the resources in the Hadoop ecospace. Then Hive. Hive is a system to process all the structured data. Okay, like database, SQL queries, they all can be done on Hadoop platform. Then there is a Pig scripting tool which will uh, reduce coding. If somebody uses Pig language, right, instead of mapper reducer programs, they will save a lot of coding time. Then there is Oozie, which is a workflow scheduler. It will schedule a lot of tasks and it will create a workflow, just like you have seen workflows in other applications, in other subjects, and so on. It will generate, or this pick can be used to generate that workflow schedule. Okay, so where tasks can be run in as a workflow, like one after the other. So after one set of tasks completes, other set of tasks uh, can be initiated and can be executed. So they all will run in a workflow. Okay, and similar to this DevOps workflow and so many other workflows that exist in so many fields. Okay, then Spark we'll see later, Flink, streaming engine, all those things we will see slowly later. But right now, these are the big data platforms that are uh, used for parallel computing and distributed computing. Okay. Performance considerations, of course, we have seen that before. So for various factors or strategies are used, where in case if the data has to be kept local, okay, how to improve the performance uh, to in terms of bringing in the data to different distributed storages and servers, how to optimize the performance, how to optimize the access time, how to reduce the latency, everything. Okay, then network shuffling, because see, every the distributed structure network is involved. Nothing is local in a distributed system. So you have to bring in the data to the and make it local to the server. So you need to use network bandwidth a lot. So and so shuffling is should be minimized. You should not be bringing the data to something, take it back and forth is not should not be done. Okay, should reduce that shuffling. You should bring in the data and do everything that is needed, then move it back to the storage. Remember that ETL thing, extract, transform, loads, all those things, right? So you should minimize all the shuffling, then push it to the data store. Then in-memory caching, which we have seen, in-memory computation, everything, they are required and they have to be used. Vectorization, GPU acceleration, all these things will improve parallel computing, load balancing, everything. So you don't want to load up one set of nodes or single node. So load distribution, load balancing is extremely important. Okay. So various applications you can read up. Then this ETL pipelines is also shown here. The extract, load, extract, transform, and load. Then there is upcoming um, trends or requirements for distributed and parallel computing for big data. Okay, something called this CXL, which we explained yesterday. CXL actually provides this memory-centric architecture. That means it will provide that memory grid, okay, and for supporting parallel computing, distributed, mainly parallel computing, okay, and for processing data on a large scale and in parallel. Okay, what this CXL uses is it, of course, it's relying on the um, this is the they are relying on the hardware. So it is basically nothing but it's Express Link. I think I mentioned it yesterday. Not remember. Yeah, here it is. Compute Express Link. Yeah. So that depends on the hardware. So it uses this PCI. This is programmable communication. Peripheral communication interface. Lots of acronyms you have to remember. So peripheral communication interface hardware, which you will see on your laptops and any servers, right? They all provide high speed link to move the data in and out. And the data should be made available in the memory. Okay, so they move the data quickly to the memory and then back to the peripherals. Okay, so all these are future trends, and big data has to support all these new architectures. Okay, memory centric, then of course you always require this scalable, low latency, all these things, distributing workloads, load balancing, all these things are required. All these NFRs I told you in the first class itself. For everything, for any solution, for any model, it has to meet this NFRs, non-functional requirements. So that's where the scalability, latency, performance, all those usability, all those things come into picture. Okay, but from big data analytics or processing point of view, all these are needed for various environments and for various use cases. Okay, so that's it for today. Where is it? Yeah. So the in memory computation, all these things I covered yesterday. So in the next class, we will move on to Hadoop. Okay. So no other topic is pending before this as per the syllabus. Okay. All right. So that's it. We are done. Take attendance. Any questions? So tomorrow we also will be online. I mean, this week it will be online for sure. So log in at the right time. Okay. Okay. Whom do we have here? Ashwini. Oh, sorry. Ashwini is there.
Yes, sir.
Here. No, I'm not going to. Yeah. Because some of you don't answer. So I just mark as per the joinees. Yeah. Joinees list. Then Dania. Okay. Joshika. Okay. Megha, Nandita, okay. Ravi, Reena, Sabrine is missing. Okay. Sheila is there, right? Shilpa is always missing, I think. Shilpa is missing. Srinidhi is also missing. Saundarya is there, okay. Saujanya is missing. Then Sri Narahari is there. Surya is there. Tejaswini is like a permanent absentee, I think. She will have problems with attendance. Then Triveni is there. Vishwas also not there. Okay. So I'll read out the absentees. If you are there, let me know. Vishwas, Tejaswini, Saujanya, Srinidhi, Krishna, Shilpayam, Sabrin. These are the absentees. Okay, there are no questions, so we close the session. See you tomorrow. Talk to you tomorrow. Okay, thank you. Bye.
Thank you.